Let's take a look at an example and get some practice using our force and electric field intensity equations from the previous videos. So for this example, we have point charges of 5 nanocoulombs and -2 nanocoulombs, which are located at points 2, 0, 4 and -3, 0, 5 respectively. For the first part of the problem, we want to determine the force on a 1 nanocoulomb point charge at the point 1, -3, 7. And for part B, we want to find the electric field intensity at that same point, 1, -3, 7. So as always, I would encourage you to pause the video and try to work the problem or set it up by yourself before coming back and watching the solution. So a good first step for this type of problem is to take our given information or our known values and sort of rearrange it to a form that is conducive to plugging into our previous equations. So let's just go ahead here and rewrite our known values or our known information so it fits a little better in those equations. So first of all, we can label our various point charges. So let me come up here in blue and let's say this is Q1, let's say this is Q2, and this is Q3. So what we can say then is Q1 is a 5 nanocoulomb point charge, and that is located by some position vector R1, which is equal to 2, 0, 4. Similar things for our other 2 point charges. Q2 was a -2 nanocoulomb point charge, and the position vector R sub 2 is equal to the vector -3, 0, 5. And then finally, for part A, we're dealing with this third point charge, Q3, which has a value of 1 nanocoulomb, and it has a position vector R sub 3, which is equal to 1, -3, and 7. So again, keep in mind these angle brackets indicate we have vectors, whereas above here, just normal parentheses is a point. Okay, so now that we've sort of rewritten this information in this manner, it's going to be easier to plug into our equations. So first we want to find the force on Q3 due to Q1 and Q2. So force, and this is essentially what we're asked in part A. So force on Q3 due to both Q1 and Q2. And so we're going to use sort of our more general superposition equation because again, we have more than just the one term. But of course we only have 2 point charges acting on Q3, so we're only going to have 2 terms from that superposition equation. And what that's going to look like is we can say the overall force on Q3, notice I don't have any subscripts here because I'm sort of combining all of the forces into one equation, is we're going to have the charge of interest, which is Q3 in this case, divided by 4 pi epsilon naught. And this is going to be multiplied by 2 separate terms. The first term is the force coming from Q1, so it's going to be Q1 times the position vector between the two, so from 3 to 1. And then we have the distance between the two, which is just the magnitude of that distance vector cubed. Okay, and then our second term is related to our force coming from Q2. So we have the charge Q2 times the position vector of R3 minus R2 divided by the magnitude of that position vector cubed. So R3 minus R2 cubed. So from here, it's just a matter of plugging in the appropriate values. For this first example, I'm going to go through and show sort of all of these steps just to make it sort of abundantly clear how we're doing that. I'm going to come down here because I'm going to need a little bit more space. So let me do the denominator first. So we have 4 pi. And then in a previous video, we said our permittivity of free space epsilon naught is approximately 8.854 times 10 to the -12. And our Q3 is 10 to the -9th. So I'm putting everything in meters, coulombs, farads. We don't have that at the moment, but basically I'm going to all my SI units. So that's why I've changed nanocoulomb to 10 to the -9th coulombs. Okay, so now for the terms in brackets, so for this first term, in the numerator, our Q1 is 5 nanocoulombs, so 5 times 10 to the -9th coulombs, and then that's going to be multiplied by this vector. So our R3 we said is 1, -3, 7, and we're subtracting from that 2, 0, 4. So again, we're going back to our vector algebra that we talked about before. And so I don't want to close that bracket just yet. And then we have the magnitude of that vector. So this 1, negative 3, 7, minus 2, 0, 4. So that magnitude cubed. And then our next term I'm going to have to put on the next line. So for our Q2, we had a negative 2 nanocoulombs. So again, notice I need to include that negative sign there. And nanocoulombs, so 10 to the minus 9th coulombs. And let me actually move this down a little so we're not mixing that up with the denominator of the above term. So this is going to be multiplied by the vector. So we have R3, which is 1, negative 3, 7, minus negative 3, 0, 5, so our R2. And let's close that. And then in the denominator here, it's just the magnitude of that vector, 1, negative 3, 7, minus our negative 3, 0, 5 cubed. And then let's close our square bracket. And so that's our force equation. Okay, so if we evaluate some of these things, we can reduce this a little bit, begin reducing this. So the term out front is approximately 8.988. So again, let me move down so we have a little more space between so we're not getting mixed up. And so this is going to be multiplied again by 2 terms. So we have our 5 times 10 to the negative 9th. And so that is multiplied by a vector negative 1, negative 3, 3. And that magnitude squared ends up being approximately 82.819. And then for our second term, we still have the negative 2 times 10 to the minus 9 times the vector of 4, negative 3, 2. And the magnitude cubed of that is 156.170 approximately. Okay, so now what we can do is we can get sort of 2 vectors. And the reason I want to do that before adding is we can look at the component due to Q1 and the component due to Q2. So the first term from Q1 is going to be approximately negative 0.543, negative 0.1628, and 1.628. And so that's times 10 to the minus 9. And then for our second term, we have approximately negative 0.460, 0.345, and negative 0.230, and this is also multiplied by 10 to the minus 9th. And again, why would I want to keep these separate? And it's just to point out that this first term, and so really all of that, including the 10 to the minus 9, is our force on Q3 from Q1. And from the second term, again, including that whole 10 to the minus 9, is our force on Q3 from Q2. And so if for whatever reason we wanted to know the force from one of several components, we could keep them separate. But of course in this problem, ultimately we're asked just for the force on Q3, so we can just add these two together to get approximately negative 1.003, negative 1.283, and 1.398. And instead of writing in the 10 to the minus 9, I can just write that this is nanonewtons. So that would be our force experienced by Q3. So now for part B, we had said, what's the electric field at that same point? And so the benefit of this is that we can say, well, we're sort of quantifying the forces from Q1 and Q2 without having to have a particular test charge there. So for part B, all we need to do is say that our electric field is equal to our force divided by Q3. And so of course what we get is this is going to be F divided by 10 to the minus 9, or we can say that's multiplied by 10 to the 9th, and we get that that is equal to approximately negative 1.003, negative 1.283, and 1.398, and the units of that are going to be volts per meter. We no longer need the nano there because we multiplied by 10 to the 9th. And so again, the benefit of having that electric field expression as opposed to the force is now we could sort of switch out and we could say For a charged particle with charge whatever, so Q4 of some charge, we could easily go and at that point multiply by this electric field value or electric field intensity to find the force experienced by that charge Q4. So we have a little more flexibility in terms of the E is more general, not for a specific point charge. So another example is on page 117 in the text. And so I've not included it here just for time, but it's sort of an interesting example where we're using our electric field to separate solids. So definitely take a look at that if you want to get some more practice, or if you just want to see sort of a cool application of these electrostatic fields.